Hello, I'm Dr Scott Steedman, and this is a series about my heroes, fellow engineers and the greatest structures they built on Earth. The tallest, the biggest, and the most expensive buildings ever built. The kind of structures that beg the question, how did they build that?
In our first programme, we travelled to Paris to take a look at the Eiffel Tower and then visit the Grande Serre, one of the finest examples of late 20th century structural engineering. But our story begins at the spectacular Garabit Viaduct in the heart of France. The development and mass production of iron and steel in the 19th century radically transformed the nature of engineering. These newly plentiful materials offered pioneers undreamt of opportunities to bridge any expanse and scale unbelievable heights. Alexander Gustav Boneckhausen-Eiffel was one such pioneer. Born in Dijon in 1832, he trained as a chemist, but a curious twist of fate drew him to the burgeoning railway industry. It was in building bridges and viaducts that he made his name, and that reputation won him a commission to bridge the gorge at Garabit.
The Garabit Viaduct, here in the Massif Central in the heart of France, was the finest of Eiffel's bridge designs. A spectacular bridge built with mathematical precision, this viaduct illustrates the best of the new, bold civil engineering which emerged in the 19th century.
The viaduct at Garabit was to be the highest iron arch bridge in the world. This design was an ideal way to span the steep gorge. A 563-metre-long railway deck sits on an enormous arch which straddles the Truyère River below. Eiffel used wrought iron because no other material had the strength and reliability to make the viaduct possible and allow the relentless progress of the railways to continue. The giant arch is pinned onto huge concrete abutments that are built onto the sides of the valley. The weight of the bridge passes down the arch into the abutments. The deck stands 122 metres high above the bottom of the gorge.
Engineers at that time did not have access to the complex computational methods of today, and they had to design a structure which they knew they could analyse. They had a shrewd idea of the direction of forces and the strength or resistance of materials, and their structures reflect that fact closely.
Eiffel opted for iron trusses for the huge arch, supporting piers and railway deck. A simple element, the iron truss is easy to analyse and can be used in almost any situation.
The whole truss has to be stiff enough and strong enough to carry its own weight and the weight of a train. The whole truss works like a beam trying to bend. So the top is in compression, it's being squashed, and the bottom is in tension, it's being stretched. The crisscross members in between work in either tension or compression, and one of their key functions is to keep the top and bottom in position. The stiffness of the whole bridge comes largely from the distance apart of the top and bottom, the depth of the truss. The bridge is made up of giant trusses, but within the giant trusses, there are also smaller trusses. It works on just the same principle. The top and bottom pieces, which carry the bending forces, are held apart by this cross-bracing in between.
All the pieces for Garabit were prefabricated, brought to the site and then riveted together.
It's like a giant Meccano set. Riveting was a skilled job. Must have been quite hairy doing it out here, this height. Riveting is a good process though, and the rust that can develop around rivets can help actually fuse it all together. It's a nice system for bonding metal. Let's go on. Eiffel was very concerned about wind forces, and he carried out experiments to determine the wind resistance of different sorts of truss. Here on the Great Arch and up there on the piers, you can see that they flare out, which gives the bridge the lateral stiffness that it needs to resist the fierce winds that funnel down the gorge. Eiffel's method of construction of the arch was ingenious, requiring no scaffolding underneath. Instead, he built each side up from the concrete abutments as two cantilevers suspended on steel cables from the piers on either side. The whole operation was extremely precise, and when they finally met in the middle, only a very small adjustment was needed. Finally, they put the deck over the top. You can feel the whole bridge vibrating under the weight of the train. Quite a funny feeling, really. Yeah, it's passed over now. Wow, that was quite exciting. Staircase is wobbling, but that you could feel these main girders vibrating quite strongly. Eiffel calculated that under the weight of a train, the center of the arch here would deflect just 8 millimeters, about that much, and he was proved exactly right. In a traditional arch bridge, the weight on top is carried down to the arch through the spandrels, the solid part between the deck and the arch, which you can see in the masonry bridges on either side. Here, solid spandrels would have been so huge that Eiffel's engineers concluded the forces would be incalculable. So they opted for no spandrels at all, and instead used this great depth of truss bent into the shape of an arch to give the bridge the stiffness it needed to carry the trains. The most dangerous moment in any construction project, in terms of the project as a whole, is often just before the construction is complete. Eiffel must have been very relieved when the two halves of the great arches were finally riveted together, and he'd accomplished his dream, the biggest iron arch bridge in the world. With the completion of the bridge at Garabit, Eiffel's reputation as one of the greatest civil engineers of his time was complete. It's a working bridge, of course, functional, like all of Eiffel's structures had been up to that time. Such a simple form of construction. Eiffel must have wondered how far he could go with it.
Paris at the end of the 19th century was the second largest city in the world, a city of wealth, a city of empire. There was a mood to celebrate the centenary of the Revolution of 1789 and France's new global status. A universal exposition of industry and commerce, a grand exhibition was launched, and it needed a centerpiece. The invention of the lift and new skyscrapers in America must have inspired Eiffel. He jumped at the chance to build a huge and lasting monument, the Eiffel Tower.
Of course, the images that we have of the Eiffel Tower are usually from a distance, and it's not until you get underneath it, like this, that you really realize how huge it is. And the feeling of space under these great symmetrical legs is very impressive indeed.
Eiffel used 250 men to build the tower, and his engineers produced over 5,300 drawings of all the component parts. As at Garabit, everything was prefabricated and all the holes were pre-drilled. Parts were then brought to the site where they were lifted into position by cranes and riveted together.
Must have been very exciting going up in the lift. They were just recently invented. Quite exciting today, really.
To a Parisian in 1889, the highest thing you'd ever have been in would be a 7-story apartment block, like the ones down here. This is a waxwork of Eiffel in his office at the top of the tower. He was very interested in scientific experiments, and one of his justifications for the tower was the study of the lower atmosphere. Although Eiffel's obviously closely associated with the tower, in fact, it was originally conceived by two of his engineers, Monsieur Koechlin and Monsieur Nouguier, who'd sketched out a scheme for a super tower as early as 1884. Of course, they were all railway engineers, really, so they used the techniques they knew best. And what this reminds me most of is a gigantic railway pier, and we're right inside it. Eiffel's tower was to be the tallest structure in the world. Only iron or steel would be strong enough and rigid enough to support itself to these heights. Steel was a relatively new material, so Eiffel opted for what he knew best, puddled wrought iron.
Eiffel had an excellent and reliable source of top-quality iron in the foundries of Lorraine. Good quality iron was important because his whole reputation depended on the success of the project. Eiffel had made a deal with the city. He would put out 5 of the 6.5 million francs it would take to construct the tower. In return, he would keep revenues from visitors during the exposition and for 20 years thereafter. It was a massive financial gamble and the biggest risk of his career. So in order to ensure a profit from the venture, Eiffel had to keep his overheads down.
And one way Eiffel could keep costs to a minimum is to standardize as many of the components as possible. Looking up to the 3rd level, you can see many of the lattice girders are identical. Under each of the main floor levels are huge girders which span across the tower, tying the legs together. That's what makes the distinctive gaps in the lower levels of the Eiffel Tower possible. Looking up here from the 1st level towards the 2nd level, you can see the 4 legs very clearly. The weight of iron in the structure is 7,300 tons, and with the lifts and the other equipment, the weight of the tower in total is over 10,000 tons. Finally, back at ground level, behind me is the base of one of the legs, disguised with stone. If we go over to the north pier, we can get a closer look at the foundations. Inside the stone base of the legs, each of the 16 ribs sits in an iron shoe resting on a concrete foundation. The shoe carries a weight of over 600 tons here, and the thickness of the iron is 100 to 150 millimeters, about the same as this thickness here. During construction, each of the ribs was secured to the foundation using these bolts to stop them bending over as they were built up. Hydraulic jacks inside the shoe were able to align the structure perfectly. C'est combien? 60. No, no, c'est bon. I don't usually go for this kind of thing, but there's something else I want to show you. The towers come to symbolize Paris, but it's the curved shape of the legs which is so well known. The obvious shape for a giant railway pier would be straight, like this. or inclined. But to resist the wind loading, these shapes would have to be braced to ground level. The wind acts on the side of the tower, trying to bend it over, just as if the tower was fixed to a wall and its weight was trying to bend it down. The curved shape of the legs acts like half an arch, carrying the force directly down to the foundation, so there's no need for bracing.
Eiffel's entrepreneurial skills made him a very rich man, but more importantly, he made a major contribution to the image of modern France, for which he is duly recognized. His tower was the last great wrought iron structure, which at the time represented the cutting edge of engineering, an ultra-modern building in a classical city. Since then, Paris has built on its reputation as home to some of the most spectacular modern structures, although iron is no longer the material of choice. On the other side of Paris, in the northeast corner of the city, is a structure that represents the very best in modern engineering. Almost 100 years after the Eiffel Tower was built, President Giscard d'Estaing decided to establish a new museum, the City of Science and Industry, to enable the French people to discover the industrial adventure of today and to celebrate the very best in modern science and technology. The museum was completed in March 1986.
This is a wonderful museum, a mixture of exhibits and exhibitionism. These great trusses on either side could have been plucked straight from the Eiffel Tower, but they look huge even for this building. But that's not why we're here. We're here to see the work of one of the greatest structural engineers of the 20th century, Peter Rice.
The late Irish engineer, Peter Rice, was one of the most brilliant of his generation. He was instrumental in the realization of projects as varied as the Louvre Pyramid and the Sydney Opera House. Rice was invited by the architect, Adrien Finsilbert, to design Les Grandes Serres, 3 massive glass houses intended to unite the museum with the park outside. The spacious units represent the pinnacle of refinement in steelwork. They are light to the point of seeming to lack substance, making even the airy structures of the Eiffel Tower and Garabit Viaduct appear bulky.
The contrast between the heavy industrial trusses inside and these beautiful, refined glass serres is total. From the engineering perspective, this is what makes the building so remarkable.
The structure of the glass houses is light years ahead of the Eiffel Tower, but still beautifully simple.
Glass is in fact a very strong material in its pure form, but in practice it's rather weak and extremely brittle and breaks in an explosive way when any scratch or defect, however microscopic, causes a stress concentration. Steel can take huge loads in tension and compression, and it has the property of ductility. It will stretch before it breaks. This gives protection against overloading, a sort of warning, if you like, that the material is about to break. The challenge is to bring these two very different materials together.
Each of the 3 serres has 24 steel frames which hold 16 glass panels, each one 2 meters wide by 2 meters high. The 16 panels in each frame weigh 2 tons.
Carrying that vertical weight and coping with the wind load from outside is what this lightweight steel frame and connections are all about.
In simple terms, the glass plates have to carry their own weight and the force from the wind outside. The glass plates hang one on another
and their weight is carried right up to the top. There's a spring up there which locates the top panel. The wind force is taken completely separately through this stainless steel cable truss. The two systems are totally independent, and they only come together in the tubular steel frame around the outside. The connection is really very clever. Inside each of these 5 points is a ball and socket joint, inside the glass here and inside this metal unit. Like a hip joint, a ball and socket joint enables the glass sheets to move independently, so the whole system is articulated. This is the tubular steel frame that surrounds the glass walls. You can see where the glass meets the building itself. There's a flexible seal, and the joint here is free to rotate, so the whole wall can move inwards with the wind.
Rice had a great admiration for the 19th century engineers like Eiffel. He talked of their structures as having a simple honesty that goes straight to the heart of the physical characteristics of the material. But his own work is more Swiss watch than railway pier.
The meticulous attention to detail and sophisticated calculation in this design allowed Rice to refine every element. Like a racing yacht, each component has a precisely defined function. There's no excess baggage. There's some irony then that in a museum celebrating science and engineering, Rice's brilliant and innovative design isn't acknowledged or explained anywhere.
Rice also believed that the role of the engineer extended to building structures that people warmed to and that conveyed a feeling of having been designed by one who cared.
Rice's genius for structural engineering is clear. He had a mission to enrich people's experience of the structures around them, which is where he differed from Eiffel.
However, both Rice and Eiffel were like artists, masters of their materials and the knowledge available to them. But new materials and techniques are evolving all the time. Who knows what brilliant structures people will be enjoying 100 years from now?
People have always felt the need to feel protected from marauding armies or the ravages of nature. When it comes to defending communities, engineering has a key role to play.
In this program, we travel to the huge Citadelle de Blaye in France to look at the work of the great military engineer, Marshal Vauban. Then we move to Holland to grapple with the task of defending a nation against the sea. But we start our story in medieval Scotland. Here on the east coast of Scotland, Tantallon Castle stands on a rocky promontory, protected on 3 sides by the sea. This magnificent castle dates from the mid-14th century, built to protect the family of successive generations of a local warlord, the Douglas Earls of Angus. The 14th century in Britain was a dark and difficult time, and those with the means protected themselves and their families by building huge castles to defend their territory against aggressors. Most people's idea of a castle is 4 walls surrounded by a moat. While many castles use nature to their advantage, at Tantallon this is taken to the extreme. With cliffs on 3 sides, they only needed one huge wall across the promontory to provide a barrier against attack. In the 14th century, the principles of defense had been unchanged for hundreds of years. Castle walls needed to be high enough and sheer enough to repel boarders, and solid enough to resist the force of boulders hurled by catapult. Just climbing up inside the Great Wall. Wonderful tower up here, absolutely amazing. His keep at the east end of the curtain wall is exactly the same width as the wall. Must be all of 12 feet wide. At 12 meters high, the red sandstone wall was an imposing feature on the landscape. With this great curtain wall to protect them and the sea around them,
The Earls of Angus and their people lived in this community for over 170 years in comfort and security. Tantallon's reputation grew as one of Scotland's greatest baronial mansions. But following its construction in 1350, gunpowder swept across Europe, revolutionizing warfare, and in 1528, Tantallon faced its first serious test.
Seeking to assert his authority over the 6th Earl, the young King James V assaulted the castle with a small force, including 3 cannon, and besieged it for 20 days. It was the first time Tantallon had been attacked by cannon. The castle survived unscathed, but it was clear that strengthening works were needed to resist this new form of weaponry. They strengthened the castle by building a new tower in front of the old one, using the distinctive green mudstone that you can see beneath me.
The green mudstone was a clever choice. It's much softer than the red sandstone and would help to absorb the impact of cannon fire. You can see how the mudstone has weathered much more quickly than the red sandstone.
This is one of the rooms which has been infilled with masonry in an attempt to increase the mass of the curtain wall. What a mess. Perhaps they were concerned that with the new cannons they would just blast through the door, and they therefore assumed that their walls were going to be strong enough. They'd add some stonework and fill in those empty rooms and so on. But they put most of their money into this piece of work here to protect the gateway. This is part of the defences of the castle after 1528. That could do you a lot of damage. It must have been unbelievable in here when that exploded.
In the years after the strengthening in 1528, Tantallon was regarded as so well fortified that Henry VIII chose it as the place to store his gold, destined to buy the loyalty of unreliable Scottish lords. But in 1651, Tantallon finally fell to one of Cromwell's armies. Continuous bombardment by 16 cannon over 12 days finally breached the Great Wall.
The reason was that the repeated impact, high-energy impact of the cannonballs on the same spot of the exposed vertical wall was inevitably going to break through eventually. Medieval design was no match for the new technology.
By the time Cromwell's army had laid waste to the once mighty defences at Tantallon, the castle was some 300 years old and hopelessly out of date. On mainland Europe, great fortresses had been built that tackled the problem of cannon fire with defences on a different scale altogether. By the 17th century, warfare on the continent of Europe was a fact of life. It was the age of the siege. The medieval castle was overtaken by an altogether more advanced concept of defense which required a new type of person, the military engineer.
It was also a mathematical age, the dawn of the age of reason, the time of Galileo, Descartes, Newton. Mathematical calculation was the key to unlocking the logical harmony of the universe. Symmetry and proportion were the key to design, and fortifications were no exception. Here at the Citadelle de Blaye in southwest France, there's a classic example of the work of one of the greatest military engineers of all time, Marshal Vauban. The primary function of the fortress at Blaye was to guard the mouth of the Gironde estuary and the city of Bordeaux upriver. Vauban's mathematical approach places him in a unique position historically, as one of the first to apply a systematic design method to his work.
Vauban was a veteran of many sieges and was appointed by Louis XIV personally to oversee the construction of a network of fortresses around the country to defend the nation against invading armies. An awesome responsibility that made him one of the most important men in the country. Castle design had come a long way since Tantallon, and fortresses now altered the landscape with massive earthworks to protect against attack. Vauban's contribution was to take state-of-the-art defense ideas and improve them by applying geometrical rules, standardizing the form and method of fortress construction, enabling the entire national defenses to be built to precise instructions.
The system of defences was highly geometric and meticulously thought out.
Blaye is protected on one side by the Gironde River. On the other side, huge curtain walls surround the fortress with triangular bastions at each corner. Bastions were huge buffers situated in front of the curtain wall. There are 4 at Blaye. Between and in front of the bastions were ravelins. These arrowhead-shaped defences were like small bastions and lower than the defences behind, enabling them to be shot over. Around the whole fortress was a great ditch. Around the outside of the ditch was the glacis, a huge mound built up and around the outside of the fortress to prevent a direct line of fire at the base of the walls. Blaye is so big that it's hard to visualize it from the ground. By drawing an overhead plan, we can also see Vauban's method for setting out the fortress. First, he laid out the corners of the bastions at regular distances. Then he mapped out construction lines between the corners, and from those lines used his standardized units of measure to determine the angles along which to construct the bastions and the curtain wall. Next, he worked out the position of the ravelins. This was determined by the line of fire from the sides of the bastions. Around the whole fortress, he built up the glacis. And added bridges to connect the ravelins to the curtain wall over the ditch.
The key difference between the medieval castle and this fortress is that behind the walls it's backfilled with earth, as you can see on the ravelin behind me. Even if you were to breach the wall with cannon fire, you couldn't just run through. It's a mountain. But these earthworks introduced a new problem, which is where Vauban made his second great contribution to engineering.
A wall retaining earth has to support not only itself, but also the pressure of the soil behind it. Too thin and it will be pushed over. Too thick and the amount of masonry will be unnecessarily expensive and time-consuming to construct.
Engineering is all about risk and return, and the price of failure in this case would be defeat in battle. Vauban was committed to building over 100 fortresses around France, so a standardized approach to design was essential. Vauban decided on a geometric solution to the angle of the wall, depending on its height and the width at the top. This is the top of the wall, the front, and the base. The back of the wall is buried, but it's vertical, like this. Behind the wall is earth, right to the top.
The slope of the wall was to be 1 to 5,
giving it the stability against overturning that Vauban required. It's hard to find anywhere where we can see the width of the wall clearly, but on top of this ravelin, we can see that the wall is 1 metre wide. It's 7 metres high. Let's go and look at the bottom. The wall's been cut through here to make a door, but we can see the back of the wall is about here, and the front is over here, and it's more than 2.5 metres thick at the bottom. From the ditch, we get a good idea of the huge scale of the construction. Vauban's works started here in 1685 and took 500 masons 4 years to complete. Fortunately, they had a good supply of stone in the local quarries. Bly was one of Vauban's early works and is remarkably well preserved. Outside lay the region of Bordeaux and the local community. Inside was the garrison, up to 1,400 men.
Bly was never taken. Vauban's network of fortresses gave France the security it needed.
Vauban's contribution was that he was the first to appreciate the problem of the pressure of earth on a wall and to propose design solutions. Today he would have been known as a civil engineer. His great insights into siege warfare come from his unparalleled experience both as an attacker and as a defender, fighting in 50 important sieges in 52 years. During his career, he built or adapted over 150 fortresses in and around France, requiring 10 million tons of masonry, a huge amount of construction work.
Vauban's system of defences and the castle in general became redundant when the invention of the howitzer enabled shells to be lobbed over the walls from a distance. Today, massive earth defences are more likely to be defending nations from nature than from marauding armies, but the engineering problems are every bit as challenging.
The Dutch people have always lived with the threat of being overrun by water. But on the 1st of February 1953, a huge storm surge took them by surprise, breaching the sea defences in 67 places. 1,800 people drowned. For centuries, the Dutch had relied on dunes and local dikes for protection from the sea, but it was clear this was not enough. The survival of a nation was at stake.
The Dutch government concluded that the entire coastline should be protected by a system of dikes and barriers to be called the Delta Sea Project. It was to be hugely expensive, but the alternative was too terrible to contemplate. The Dutch have a long history of dike design. Dikes have to support not only their own weight, but the force of water against them. Any weak spot in the dike and the whole system of defences can crumble.
The big question is how high the dike should be. In 1953, recognizing the problem of rising sea levels and the unpredictability of great storms, the Dutch government opted for a level at least a metre higher than the terrible flood. There was a huge amount at stake. The length of the coastline is enormous. A balance has to be struck between the cost and time of construction of a high dike and the value you place on people's safety. It's a tough decision, whether it's your own home or your country that's at stake.
One of the last closures was the most difficult of all, the estuary of the East Scheldt, or Oosterschelde. The original plan was for a dam to keep out the tide, but this would destroy the sensitive ecosystem of the estuary. Instead, the Dutch opted for a vast barrier with gates that could close in the event of a storm surge.
The strong currents and the shifting sand in the East Scheldt made the construction of the barrier extremely difficult. As you'll remember from walking on the beach, when you fiddle around with your feet in the sand, you sink in, and the sea can easily wash it around your feet. So you need to densify it, you need to compact it first of all, to provide the base that you need for a great structure like this. And that's exactly what they did.
The contractors compacted the seabed and laid a vast mattress of stones and sand to provide a solid foundation on which to place the 65 piers that link the barrier gates over a distance of 3 kilometers.
For almost all their lives, these gates will be open, and the sea is free to pass in and out of the estuary beneath us. But when the storm surge comes, the gates are all that is between the people of Holland to my right and the sea out there. They have to work. Like a guillotine, each of the 500-ton gates is lowered into position. They'd have a lot of warning, maybe hours, of the arrival of the storm surge, but they can shut the whole barrier in 90 minutes. Of course, it doesn't have to be watertight. They only have to hold out the surge during the high tide. After the tide has passed, then the danger has receded.
Thankfully, the gates have never had to be used in anger, although they have a drill every year to make sure the gates will function in the event of a surge.
Behind the huge black gates here, with the estuary to my left and the sea out there, we can see the top of the great concrete piers. Each of them is the height of a 15-story building, but there's only a quarter visible above the sea. The water here is up to 30 meters deep. The piers support the machinery for the gates up there and a concrete road bridge over here.
The gigantic piers are hollow and were constructed in huge dry docks before being floated out into position. The construction and installation of the piers took over 4 years.
There's 18,000 tons of concrete in each one. At the base, they're shaped like a gold ingot lined up in this direction to give them the stability against the storm forces from the sea. Once they were in position, they were sunk onto the seabed and ballasted with another 12,000 tons of sand in each one. To protect them against scour from the tides, they imported at huge cost stone from as far away as Finland. It took 5 million tons to cover the entire 3-kilometer length of the barrier. But the biggest challenge was to align them perfectly within centimeters to allow the great steel gates to go up and down. Out here, practically in the open sea. Oh, it's windy. This is the base of the hydraulic cylinder and the piston that holds the gate up in position in its normal state. It's connected to the gate by the giant pin down there. So when the gate's triggered, the whole thing drops into the sea. Whoosh! Brilliant. The framing on the front of the gate gives it the stiffness that it needs against the force of the storm surge. It's very dramatic. You can see the tide now driving in underneath it. The tide's now going at full tilt, and you can really get an idea of the forces on the concrete sill beneath me and on the piers and on the stone out there in the sea. Just imagine that huge weight of water flooding through. In fact, it's very like what would happen if a dike was breached. You could imagine that flooding a polder in no time at all. And if you think this is exciting, on the last pier there's a marker where the 1953 flood level in this part of Holland reached. We're a long way below it today, luckily.
The barrier was completed in 1986 at a third of the cost of the entire Delta Sea project and 3 times as much as the cost of a simple dam. But it's a testament to modern civil engineering, providing defence for the people of Holland while maintaining the natural habitat of the tidal estuary.
Not many countries can afford the Dutch approach, but balancing the environmental issues with society's aspirations for security, whether physical or financial, is at the heart of the civil engineer's role throughout the world.
One thing is for certain. The battle to ensure the survival of the human race as our environment continues to change means the civil engineer will remain on the front line, defending us from the elements.
Throughout history, there's been one form of structure synonymous with great public events. It's the dome. Domes have an almost mystical ability to create a sense of awe in the humble visitor. And to engineers, meeting the demand for ever larger domes has been an enduring challenge. I'm in London at the site of the Millennium Dome, and in this programme, we'll explore the mystery and the glory of this and two other great domes. But we'll begin in Florence.
No other city in Europe, with the exception of Venice, trades off the past in the way that Florence does. In addition to its fantastic array of buildings, the list of geniuses who lived and worked here reads like a who's who of art and literature. Dante, Michelangelo, Botticelli and Giotto, to name but a few. But to any visitor like me, picking their way through the Florentine streets, there is one incredible building tantalizing you on every turn. It's dominated the skyline of the city for over 500 years, the spectacular Duomo by Brunelleschi. In a design which brought together science and art to create a new standard for the future, the dome of the Cathedral of Santa Maria del Fiore marked the arrival of the Italian Renaissance. In completing the building, the city of Florence announced to the world that it could equal and even outdo the greatest achievements of the Roman Empire.
The cathedral itself, begun in 1296, took 50 years to complete, and that didn't include the highlight, the soaring octagonal dome.
At that time, domes were built by supporting the underside with timber scaffolding. But in Florence, the span was so great that no formwork could bridge it completely, so the cathedral had to go domeless even after completion in 1357.
Quite simply, they'd started a project with no idea of how to finish it, and it was to be another 60 years before a competition was launched in 1418 to find a viable design for the dome.
The winner was Filippo Brunelleschi. Armed with a 12-foot diameter model and a series of impressive innovations, he eventually won the contract that would take a further 16 years to complete.
Brunelleschi's major achievement was to complete the dome without any timber supporting structure. He argued that a dome built up in stages, in rings, would be entirely self-supporting. This technique had never been used on this scale before. Although there was no timber structure supporting the roof, Brunelleschi built a working platform for the masons, cantilevered out on great wooden beams socketed into the side of the cathedral here. There are 48 of them right round the wall. The holes are huge. Imagine what the beams were like fitted in there.
One major innovation was a double skin. The dome has an inner and an outer shell. But at over 4 meters thick, it is also extraordinarily heavy, weighing 25,000 tons.
You see, domes carry their weight downwards and outwards, and they need to be buttressed or supported around their perimeter to stop them cracking vertically.
Historically, great domes had been buttressed around their sides, and here in Florence, there are 3 small domed apses which provide some support.
Brunelleschi realized that this support was not enough. He used a system of stone chains with iron links like this around the perimeter of the dome, tying the whole structure together.
But all these systems were not sufficient to stop some movement from taking place, and you can see cracking up the middle of several faces.
People often think of cracking as evidence of imminent collapse. It may not look perfect, but masonry can really take quite large movements before it actually falls down.
It's incredible. Vasari's frescoes really use the octagonal shape. Hell portrayed at the bottom, moving up through heaven, and topped by that fantastic false lantern. Access to the interior of the dome is by a sequence of staircases up through the stonework.
I've climbed right up inside Brunelleschi's dome, between the inner skin and the outer skin. The bricks have a very distinctive herringbone pattern, like the Romans used. Let's go on round the dome, through one of the great internal ribs between the inner and the outer shell that helps to stiffen it, and the dome stretching away above us. Fabulous. Look, and here's a window. You can see right down inside. The inner skin is really thick here, over 2 meters thick. You can see how clearly the masons have laid the bricks downwards in a line that lines up exactly with the bottom of the dome over there. It's just fantastic to be inside here and see this structure. I'm right inside the lantern at the very top of the dome. The lantern lets light down into the cathedral down there. Domes may look a bit like arches, but it's here we can see the fundamental difference. An arch always has a keystone right here in this space to stop the 2 sides falling in. A dome can have a hole because the forces are spread throughout the shell.
However, Brunelleschi's octagonal dome was an extra challenge. Smooth, rounded domes can carry their weight more efficiently and can be much thinner.
But in the end, it's the great thickness of this dome that makes it work.
Looking at the structure now, its 45-meter span could be considered modest in today's terms. However, for the best part of 400 years, the Cathedral of Santa Maria del Fiore had the largest dome in the world. An amazing and unique achievement, the dome still dominates the city skyline in a manner unequaled anywhere else and is recognized worldwide as the greatest masonry dome in existence.
The method of construction used here set a pattern which continued right up to the building of the great cathedrals of St. Peter's and St. Paul's. It's only recently, with the advent of new materials, that domes and their design have undergone some radical and spectacular changes.
This is La Défense in Paris, a city as famous for its more recent innovative architecture as for its traditional buildings. Steel and concrete, glass and fabric are the materials of this modern development. But there's one building in particular I've come here to see, a classic of design dating from the 1950s, which shows just how modern materials can reshape the traditional dome. This is the Centre des Nouvelles Industries et Technologies, known locally as the Knit Building. It was conceived as an exhibition space for French industry, built to show off France's engineering and scientific prowess in the booming 50s. More recently, it's become a retail development, housing shops and hotels.
What we're interested in is the futuristic design of the roof. While it's not a traditional dome like the Duomo in Florence, its rounded shape means it still works as a dome. It's also much thinner. In proportion to its span, it's as thin as an eggshell.
The steel and glass walls don't take any of the weight of the roof. They were part of the redevelopment of the building in 1988 and are there simply for aesthetic reasons. And of course to keep out the wind and rain. It's quite breathtaking to see it for the first time, like the vault of some giant Gothic cathedral. In essence, it's triangular in shape, with the weight of the roof channeled down to abutments buried in the ground at each corner. The sides soar up and over the top, giving it a clear span on each side of 218 meters and a height of 50 meters.
And there's only one way to get to the top. I'm right at the top of the roof, and what strikes you immediately is the huge, magnificent Grande Arche de la Défense right beside us. And here the great curved roof of the Knit building stretches away beneath us like a cloud, a great snowscape. This is the wall between the two panels, the crown wall, which carries the huge compressive force as they lean together. Let's go on.
In great buildings like this, there is always a strong relationship between the architecture and the engineering. The concept of this roof was easy to draw, but much more difficult to build. In the end, it was a French engineer, Nicolas Esquelin, who came up with the solution that we see today.
It was built in sections. First, the 6 curved panels, which meet here in the middle, and then the next 3 on either side, and finally the last 3 right out to the edge, way over there. Let's have a look inside. Inside the roof, you can see that it's made up of 2 shells, just like the Duomo in Florence, but they're much, much thinner. They're made of reinforced concrete, and down at the bottom, they're 600 millimeters thick. But up here, they're just 60 millimeters thick. That's this much.
The ribs between the top and bottom shells run all the way down to the corners. With the cross walls, they form a honeycomb, very stiff and yet lightweight.
Of course, it's not built up using bricks like the Duomo. Instead, they poured concrete onto curved wooden shutters supported on scaffolding underneath. It must have been a colossal undertaking.
To keep their shape, all domes require secure foundations, and the Knit dome is no exception.
The weight of the roof is channeled down the 3 sides to the ground. As the dome tries to sag, it pushes outwards at the corners, and the force outwards at each corner is equal to the weight of the Eiffel Tower.
Inside, the shape of the vaults reminds me of 3 colossal fans meeting at the top. It's quite spectacular. The curved shape of the panels is also very distinctive, and it's there for a good reason.
You see, the thin panels in the roof have to carry a lot of force along their length, all the way down to the ground. The problem is that a flat panel would buckle easily, like this. But if you make the panel curved, like that, then it's much stronger. And that's the principle they used here. Neat, isn't it?
It's a bold design, even today. And like the Duomo, persuading people that it would stand up was a triumph, even in the 1950s. While the Knip building doesn't look like a dome, the main reason that it stands up is because it is a dome structurally. The forces are spread down through the roof.
So domes don't have to be round, and they can be very thin. In fact, as domes get larger, they have to get thinner to be economical. But if you want to make them really large and really thin, they have to work completely differently. The Millennium Dome at Greenwich in London is the largest dome in the world. But it's quite unlike the more conventional dome structures we've seen. It's very thin and it seems to hang in space, held in a cat's cradle of steel wires. But is it really a dome?
Well, it's clearly dome-shaped, but the forces at work in this structure are the opposite to the domes in Paris and Florence. Instead of forces pushing from the top down, this dome is being pulled into shape from the base.
The shell of this dome is in tension. Unlike our previous domes, whose shells were self-supporting, the Millennium Dome is held in shape by its masts and cables. Basically, it's like a tent.
Construction began on the 23rd of June, 1997. It was a mammoth job to organize the people and equipment required to build the dome on schedule. The concept of the dome came about only recently. In 1996, a series of exhibition structures were being developed to celebrate the millennium, but it seemed inefficient to make each of them weatherproof, particularly if they were only going to be temporary. Covering the whole show under a single umbrella would create a focus and simplify the design of the individual exhibition stands inside. So the idea for the Millennium Dome was born.
A year on, and construction of the main structure is nearly complete. It's an incredible achievement to have got this far, this fast. It's a huge building site at the moment, and it's a fantastic time to see it, because when the exhibition is in place, it'll be very hard to see the structure. The dome will be twice as big as the Georgia Dome in Atlanta, 320 meters in diameter, and the perimeter is 1 kilometer long.
The most dramatic feature of the whole structure for me are the cables, which form a giant net in the sky. Around the opening at the top is a tension steel cable ring. All the cables pull outwards on this, and it's vital to the stability of the whole dome.
It was particularly important to make sure that any damage up there did not result in the whole tent unzipping. They managed this by using 12 intertwined cables so that even if one broke, the others would be able to share the load.
These are the stringers which radiate out from the center. Other cables hold them firmly in position at intervals of 25 or 30 meters.
To keep the stringers taut, they're stretched to 2/3 of their peak tension, a load of 40 tons in each cable. This means that they're virtually straight between their supports, which in turn makes it easier to hang the fabric panels. When any material is stretched like this so tight, there is a risk that a panel rips and then it might overload the next panel and so on. So to protect against this and to stiffen the structure around the perimeter, these stringers are linked by cables which run right around the dome in a circle. But, and this is a neat trick, they couldn't lie in the fabric, so they are held up above the panels using these rigid wishbones and crisscross cables. Each of the masts is 100 meters high, and they do all the work to hold the dome up. The weight of the dome isn't great, but the masts must collect and channel all the tension forces down to the ground. Each mast carries a compressive force of 1,000 tons, spread down through these 4 struts at the bottom and carried into the ground through the concrete foundations. These backstays hold the mast in position and tension it down to anchors under this concrete block, screwed into the ground like giant tent pegs. The mast is trying to pull up on the anchors back towards the dome, and this concrete slab helps to hold the anchor in position, pushing out from a giant concrete ring beam all around the perimeter. The fabric which has been chosen for the dome had to be translucent, strong, and long-lasting. It's a glass fiber material, coated in Teflon and only 1 millimeter thick. Compare that to the 4-meter thick shell of the Duomo in Florence. There were other cheaper choices, such as a PVC-coated polyester, but it wouldn't have been so long-lasting and it would have absorbed dirt. This should remain cleaner for longer. The Millennium Dome is a landmark in the history of engineering achievement. It's a structure which could not have been built even 20 years ago. It reflects huge advances in computer techniques and material development, which are all part of the excitement of building. But in the end, this dome is all about celebration. For good or ill, it reflects our time in that it is adaptable, temporary, and built to mark a specific moment in history. So the Millennium Dome is very much of its time, both in its engineering and in its function. As we've seen, domes are all about communal space, bringing people together. Their very shape inspires a sense of wonder, grandeur, and security. And that's why, for thousands of years, we've continued to build them, ever bigger. Sometimes buildings seem to defy gravity. In this program, we're going to look at the ancient Leaning Tower of Pisa, the incredible Puerta de Europa towers in Madrid, and a modern classic, the Torre de Collserola in Barcelona. Buildings and structures rely on their foundations to keep them upright, and their foundations rely on the ground beneath. The challenge is to find a solution which uses the ground effectively and doesn't overload it. To explore this subject, we're at the site of one of the most famous structures in the world, in the beautiful Italian city of Pisa. The Leaning Tower is the campanile or belfry of a large complex of religious buildings, including the great cathedral, the baptistry, and an ossuary dating from the medieval period when Pisa was at the height of its power. Built to a height of 179 feet, the tower is essentially a hollow cylinder containing a spiral staircase that ascends to the bell. Both the inner and outer surfaces are faced with white marble. Construction on this remarkable building was begun in 1173 by Bonanno Pisano. At that time, the sea was a lot closer to the town than it is today, and Pisa was a rich and successful naval republic. The bell tower was to be one of the tallest campaniles in the land, to call the Pisans to worship.
Records suggest the building began to lean as soon as the first floor was completed. What is known for certain is that building work stopped in 1178 after reaching the 4th floor and was not started again for 100 years. The Pisans had to go to war with Genoa.
The reason for the tilt lies in the soil beneath the tower. The soil here is a soft clay, highly compressible and sensitive to changes in groundwater level. In this case, that means changes in the sea and the river, and crucially, from the effects of the construction of the then new cathedral just over there. It was a bit like trying to build a tower of bricks on a soft mattress.
By the time the construction had reached the 4th floor, its weight was 9,500 tons, and one side had gone down ½ meter relative to the other.
It's such a strange feeling on the staircase, because here on the south side, it's as though the stair is leaning away from you, and suddenly you climb around the corner, and the stair is absolutely precipitous. It's nearly vertical. As the soil consolidated over time, more on one side than the other, it became stiffer and the direction of lean changed from the north to the south. But nevertheless, they kept going. Construction was restarted in 1272 by Giovanni di Simone.
After 6 more years of building, the tower weighed 13,800 tons, and the settlement on the south side had reached nearly 1 meter. The bell chamber was finally built between 1360 and 1370, but to make the bells hang straight, the bell chamber obviously had to be vertical.
Here on the overhanging south side, there are 1, 2, 3, 4, 5, 6 steps up to the bell chamber. But here on the opposite side, there are just 1, 2, 3, 4 steps up to the same chamber. This is what gives the upper part of the tower its characteristic curved shape. It's an extraordinary structure, a real achievement for its day. Today we understand more about the properties of the soil below and the stability of the tower, but to the Pisans of the 13th and 14th centuries, their moving tower was nothing short of a miracle. It was a sign that God was on their side in the wars with Genoa, a sacred icon, a place of pilgrimage. As we come around the side of the tower here, we can see where the stone's been pulled apart by the tower leaning over. Masonry is an incredibly robust medium, and this is just a perfect demonstration of that. Here there are cracks opening up and then closing, and here the stone's been actually chipped off in the corner where it's been forced together. Lovely. Over the centuries, as the tower continued to lean and sink, it pushed up a mound of earth on this side, which helped to slow up the movement. Amazingly, to reveal the stonework, this was excavated in the 1830s, after which the rate of lean increased dramatically.
In 1990, it was recognized as a danger and was closed to the public. At present, the tower leans some 15 feet from the perpendicular, putting huge stresses on the south side. The tilt is increasing all the time, and in the early 1990s, the tower was also found to be rotating.
Works are now in progress to stabilize the tower for good. The Italian government was finally spurred into action following the collapse of a civic tower in Pavia. The first step was to secure the tower temporarily.
Tons of lead weights were attached to the north side in an attempt to stop the tower from leaning further. But a more permanent solution was required.
The only sensible solution to stop it falling over is to change the angle of the tower. Early schemes proposed props, but it would be very risky to work under the leaning side. The solution that's been adopted is neat and simple and doesn't even involve touching the tower. Small volumes of soil are extracted by drilling down under the tower from various points around the north side, leaving tiny cylindrical cavities. These then squeeze shut due to the pressure under the tower. By choosing in which areas to excavate, the tower can be steered back from the brink.
If successful, and trial results are so far looking positive, the repairs will extend the life of the tower by 200 or 300 years and should stop the rotation completely.
The aim is to reduce the angle of tilt by ½ degree. That's just about ½ a metre at the top. Of course, they don't want to straighten the tower completely, because at the end of the day, it's the lean that brings the visitors.
The medieval masons must have been in awe of their moving tower, not understanding the subtle movements in the soil beneath. Pisa lost the war with Genoa, but its tower has assured its place in the world.
But what if you really wanted to design a leaning building? Well, that's exactly what's just been done recently in Madrid.
The incredible twin towers of the Torres Puerta de Europa straddle the main road north out of the city. Translating as Gateway to Europe, the towers are both office blocks, one occupied by one of Spain's major banks. For me as an engineer, these structures are simply unique.
Wow. They're absolutely fantastic. Look at these huge, great black towers leaning right over the road to Madrid. Each one leans 3 times as much as Pisa, and they're twice the height. Not a lightweight piece of architecture, this. It's a really powerful statement.
But these buildings aren't just Latin exuberance. There's a good reason for their extraordinary design.
At the planning stage, restrictions on the site meant that the towers had to be 140 meters apart at the base, potentially diluting their impact if they'd been ordinary vertical buildings. The architect decided to link them visually by leaning them together. It's a bit of a stunt, but it works. They really dominate the whole space. Incline buildings are very unusual and they require special engineering design. But the principles are simple. The most critical question is the most obvious. How do you stop them toppling over?
The overhanging upper stories want to tip the building forward, so the simplest solution is to weigh it down at the back in the foundations.
Down below me, under each basement, is 14,000 tons of concrete, acting exactly like the lead weights in Pisa to counterbalance the lean of the building. That's enough concrete to cover this entire area 10 meters deep. So the counterweight stops it toppling, but what stops it bending and sagging? Every building has to be stiff enough to hold its own shape, but in these inclined towers, the problem becomes even more acute. The steel and concrete frame of the building has to form a rigid skeleton holding it upright. So the shape of the frame is very important.
The great silver triangular shapes that you can see so clearly on the side of the building give it a lot of stiffness. Triangle shapes are useful in building frames.
And I can easily show you why by sketching it. Use a napkin. Imagine a 3-sided shape and a 4-sided shape, and we try to squash them by applying forces at the corners. The 3-sided shape stays rigid because none of the bars can move anywhere. but the four-sided shape is easily flattened. So the triangle is a much stronger shape in structural terms.
The problem of the building sagging is most serious during the construction of the frame, before the building has its full stiffness. So to correct this, there's another system to keep it stiff.
Imagine my arm was the building. If I stretch this rubber band, it pulls my fingers back and straightens and stiffens my arm. Down the back of the building here, there's a system of steel cables running from the top to the bottom, anchored to the foundation, which does exactly the same job.
During construction, by tightening up the cables, they use them to straighten the top of the building by 150 millimeters. And if they need to, they could still tweak it further today. It's called post-tensioning. If you look at the space between the top and the bottom of the building, there's only a few meters in which they overlap. It's in this space, between the top and the bottom, that a huge concrete backbone supports the construction.
Wow, and here it is. The concrete core is huge at the bottom of the building, and it also houses the lifts. Let's take a trip up. Here at ground level, you can see the street outside. The lifts are at the front of the building. We'll see what happens when we get to the top. Right, here we are. At the back of the building. There. Well, this is the top of the highest building in Madrid, and there's a heliport here. Isn't it fantastic? What a view!
When they were completed in 1990, the Torres Puerta de Europa instantly became a landmark in Madrid. It's a distinctive gateway which dominates the local skyline.
Office buildings so often put costs before creativity. Most are very bland and boring, but it's really refreshing to see something so original. For the engineers, this must have been a very exciting project.
As we've seen, keeping a tower standing upright is all about controlling the forces going down. But across Spain, in Barcelona, we're off to find a fantastic expression of this. Barcelona has an impressive array of wonderful architecture, combining traditional Catalan buildings with flamboyant new design. Commissioned in the run-up to the Olympics in 1992, the Torre de Collserola is a state-of-the-art telecommunications tower.
Wow, fantastic. Coming up out of the city into the Collserola Park, green trees and a blue sky. You can really appreciate the stunning beauty of that white tower. 288 meters tall, it's almost as high as the Eiffel Tower, on top of a mountain.
There are 13 floors, all but one designed for satellite dishes and transmission equipment. In fact, the tower is big enough to house 700 people and relies heavily on brilliant engineering to keep it upright.
Traditionally, communication towers have mostly used open steel lattice structures, like the grey electricity pylon behind me. But if the new tower had been built in this style, it would have required an enormous base, and it would have looked like a giant industrial pylon, totally incompatible with Barcelona's stylish image. The city saw the new tower as a chance for something much more unusual.
A British architect, Norman Foster, won the commission. His design reduced the structure to its bare elements. The tower is a simple, hollow, circular concrete shaft. 13 floors are wrapped around it and held in place by a system of steel trusses and cable stays. Above the concrete shaft, an 80-metre telescopic steel tower, like a car aerial, reaches skywards. Right at the top sits a small crane for lifting equipment up and down.
Under the bottom of the tower, down there, the main foundation is a simple concrete disc, 20 metres in diameter and just 5 metres thick. It didn't need to be thicker because the tower is founded on rock, not soil. But such a tall, thin shaft would be much too flexible without another system to stiffen it. So the tower uses steel cables, like guy ropes, to hold it down, counteracting the effects of one of the major threats to towers, the wind. Up here, wind gusts can reach very high levels. The wind is known as the tramontana, and it blows from the northwest, rushing over the hills. Gusts can reach well in excess of 100 miles an hour. That's pretty serious. 3 sets of high-strength steel cables anchor the tower down to huge concrete blocks like this, each one 800 cubic meters, 2,000 tons of concrete.
The cables are tensioned so that even in a high wind they will never go slack, and that ensures the tower remains stiff.
In a 60-mile-an-hour wind, the top floor will move only 85 millimeters. That's just this much.
The huge forces in the steel cables pull down on the tower and up on the concrete foundations simultaneously. But any long tube under compression bends easily, so it needs to be braced.
The tower is a hollow shaft like this piece of tubing, but if I compress this between my hands, it bends and collapses easily. So how did the designers get around this when it came to the tower? Here we are on one of the floors of the tower that's still being fitted out. It's a curved triangle in shape, held up at each of the corners by a giant steel frame. The frame's pressed onto the tower by the cables which run down below and up to the top. Remember the tube? The frame acts like a brace around the tower, just like this, making it much stiffer.
Notice how lots of shapes in the structure are triangular. As in the towers of Madrid, this is where the tower gets much of its strength and stiffness.
There's a lot of equipment on the tower. This floor's for television. Each of these is a different local station. This one's for picking up outside broadcast units. Hope we don't get in the way.
You may be wondering how they built a 13-story block way up here. Well, the answer is they didn't. The floors were actually built on the ground and lifted up here by jacks. It took 4 days to lift the structure into place.
Finally reaching the top floor, inside the concrete shaft, stretches way above us. But we can't get out that way.
These cables from the top of the frame to the top of the tower cross in front of the microwave dishes. They're made of Kevlar, an immensely strong man-made fiber, as strong as steel. But unlike steel, Kevlar cables are invisible to radio waves. We're 155 meters above the bottom. This great tower is quietly buzzing away. But all around us, these cables, the steel frame, and the concrete shaft are all carrying huge forces, locking this extraordinary structure into its exact position. It's a masterpiece of engineering. There's no doubt that the tower met with the city's brief to construct a monumental technological element. The tower is unquestionably a dramatic symbol of Barcelona's commitment to innovation.
Engineering is the art of the possible. To make the Leaning Tower safe for the future, to break with convention in Madrid, or to combine beauty with function here in Barcelona, all have taken extraordinary ingenuity. And that's what it's all about. The sea can be one of the most hostile environments known to man. Storm winds, huge waves, and salt water all take their toll on any structure, either here on the coast or out there. To cope with these threats, we've had to find solutions.
In this program, we investigate the gigantic floodgates protecting Rotterdam in the Netherlands. Visit the Troll offshore platform, the largest structure ever to be moved across the face of the Earth. But we begin in Devon, southwest England. Plymouth is an historic naval city and fishing harbour in the southwest of England. It stands at the entrance to the English Channel in one of the most exposed corners in Britain, and therefore it's no surprise that for centuries its treacherous approaches have been protected by a number of lighthouses. We're off to the site of the famous Eddystone Lighthouse, which lies 14 miles out on the Eddystone Reef. The Eddystone Reef is the site of several historic lighthouses, and it's their changing designs that reflect our increasing ability to withstand the elements. There has been a lighthouse at Eddystone since 1699, but the ferocity of the weather in the Channel has claimed 3 of them. Indeed, one was completely swallowed by the sea in Britain's worst ever storm in 1703. The present tower was built by James Douglas in 1882, but it's one of its predecessors, that of John Smeaton, that we're interested in.
The first lighthouses on this site were built of wood. The men who built them advocated wood because of its flexible qualities, but they were either lost to sea or burnt down. John Smeaton's tower, built in the 1750s, was a much greater success. You can see the remains of Smeaton's tower here, near the base of the new tower. The rest of it was taken back to the mainland, stone by stone, to be preserved.
The current tower, now over 100 years old, remains unscathed by the elements, but the reason for its survival can be attributed in part to the pioneering work of John Smeaton. This is the Smeaton Lighthouse, which was brought back from Eddystone Reef and rebuilt after it was decided that it be replaced by a taller tower. Smeaton proposed a building which was said to be based on the shape of an oak tree. He said, "My main aim is to construct a tower whose every part should be strong in direct proportion to the stress it's likely to bear." Smeaton also pioneered new materials and construction techniques, inventing a large crane for lifting the large stones from a boat moored next to the site.
However, his major contribution was to recognize the importance of interlocking the stones to give the tower additional strength. The intricate shapes fitted together a bit like a jigsaw puzzle, using dovetail joints and iron and marble dowels to lock the whole structure together.
The higher up the lighthouse you go, the thinner the walls become. They are made from a granite called moorstone, which is very dense and resistant to weathering. Here at the top of the lighthouse, the keepers would ensure the flame burned constantly throughout their long stays. This frame held the candles, one in each of the holes.
Smeaton's Tower on the Eddystone Reef was finished in 1759, 3 years after starting work, and its 24 candles burned in this lantern for over 100 years. In its day, it had to endure force 12 storms, and at one time, according to the keeper in 1824, the water came from the top of the building in such quantities that we were overwhelmed.
What finally overcame his structure was the rock it stood on. Storms undermined the rock foundations, and by 1877, Smeaton's Tower was finally retired. As an acknowledgement of his great achievement, the tower was rebuilt here on Plymouth Hoe. Lighthouses need to withstand the sea, but they could never claim to hold it back. For that, something truly amazing is required. To the east of the English Channel lies the North Sea coast of Holland. With much of the country below sea level, the Dutch live under the very real threat of disastrous flooding, and much of the coastline is protected by a series of fixed barriers and dikes. Rotterdam is the biggest port in Europe, and the problem for the government was how to protect the city from the might of the sea, while keeping its main waterway open for the hundreds of ships that passed down it every day. The solution was a pair of huge floodgates that, in the event of an emergency, will swing out into the waterway and meet in the middle, stopping the sea in its tracks.
The barrier was opened in May 1997 at a cost of £400 million, and it's beautifully simple in its operation. It comprises two enormous, identical gates which are floated out from dry docks into the river and sunk onto the river bed. This is the gate on the north side, and I'm walking along the sea wall. On my left is the giant truss that holds the wall in position, and the joint that holds the whole gate to the shore. The sea walls are 210 meters long and 22 meters high. You can see about half of them here. The other half is down in the dry dock. They're hollow, so they can be floated out into the river like a ship, where the two halves meet. Then they're ballasted with water and they sink to the riverbed. We're lucky today that the dry dock's empty, so we can get right down into the bottom and have a look at the shape of the seawall and how it's floated out. But it's pretty muddy down there, so I need some boots. One of the great advantages of the dry dock for this design is it means that the maintenance is much easier. Right, let's go. Fantastic. You can see right underneath it. Here we go. Ah! If a storm surge arrives, then the whole dry dock is flooded, the wall floats up and is pushed out into the river. After the storm has passed, they float the wall back into the dock, sink it back onto its supports, pump the water out. The mud comes in when they open the gates as well. Let's try and see the shape of it a bit better. When it's out in the river, it sinks like this onto the seabed because, of course, it's held right back on the shore. So it's floated out, and then it sinks onto the seabed. And the great wall here provides the main barrier to the storm wave coming up the river. But when we get right underneath the wall, we can see the ceiling edge where it sits on the bottom of the river. And this is it. This rubber piece here, which runs right along the bottom of the wall, is what sits onto the concrete sill at the bottom of the river. It gets squashed under the weight of the wall above, and it's sitting on pistons, so it can just squidge up a little bit and provide a really good seal underneath the whole wall. Behind the gate there is the river, way up there. And these great ports are where they let the water in to fill the dock. Perhaps we'd better go. Let's go up onto the back of the wall and we can see how the force is taken out to the shore.
Supporting the Great Sea Wall is a huge truss. There are 8 main struts which take most of the force from the sea and carry it directly along the arms into the foundation. Other smaller struts above provide bracing against the whole gate twisting.
Each of the gates is the size of the Eiffel Tower lying down, but they weigh twice as much. The arms are made up of giant trusses, here made with cylindrical steel tube, all welded together. The 2 great arms that hold the seawall meet here. Their great length and the huge forces in the members mean that they're susceptible to buckling, so the trusses are very deep and heavily braced.
At the end of the gate, where the arms come together, is the pivot mechanism around which the whole gate moves.
Wow, absolutely gigantic. The huge force from the seawall is carried down through that giant truss and ends up here on this knuckle, this enormous ball joint. It's 10 meters in diameter, the biggest ball joint in the world. Under a storm load, 35,000 tons of force arrive right here. Climbing down inside the ball here. There we are. This is right inside the ball itself. It weighs 680 tons, and of course it can't be left just to sit on its socket when it's not being used. So these great pistons, 6 of them, can lift the whole ball up when it needs to be painted. Keep your fingers out of there. The whole ball turns on these bearings here when the gate is closed, bringing the face of the ball into the great grey socket that you can see behind me. Under the storm force, there's a huge pressure on this face. The pressure on the face is the same as a submarine would feel 1,800 meters underwater, 6,000 feet down. That huge pressure is passed through the steel shoe and into the concrete foundation here. And the whole foundation would give about 200 millimeters when the gate is closed. It's absolutely amazing. Rotterdam's storm surge barrier is engineering on a grand scale, ingenious in concept, beautifully executed and immaculately maintained. But both our structures so far have been land-based. If we're talking about the sea, we'd better get out there.
Off the coast of Norway, beneath the North Sea, lies the Troll Field, one of the richest areas for oil and gas deposits in the world. The challenge is to build a structure that can stand firm in the deep sea and against ferocious storms while providing a platform from which to tap the vast resources below the seabed. We've come to Bergen in Norway to go out to Troll A, a gas platform and the tallest concrete offshore platform in the world. The potentially dangerous journey out into the North Sea is only possible by helicopter, and so it's necessary to don a survival suit for the flight. The Troll field lies 60 kilometers from the Norwegian coast, and the natural gas beneath it was created more than 130 million years ago. The immense amount of gas in the field meant that a permanent structure was needed, one that would stand in place and extract gas for over 50 years.
And there it is. Isn't that fantastic? 4 great concrete legs coming out of the sea. What a sight.
The drilling deck and superstructure of Troll A sit on 4 massive concrete legs that reach down over 300 meters to the seabed. The base of the platform is made up of 19 concrete cells that were built on land. The base was towed out by tugs and sunk into a deep fjord where the 4 towering legs were added. At 369 meters, each completed leg of Troll A is taller than the Eiffel Tower. The whole structure was then sunk further down into the deep fjord, and the platform was aligned over the top using barges. Water was then pumped out of the structure, allowing it to float up a matter of centimeters to meet the platform. The completed structure was then refloated in preparation for the journey out to the Troll field. The platform was towed out to sea, making it the largest structure ever to have been moved across the surface of the Earth.
Up here on the helipad, I'm 76 meters above the sea. It's easy to forget that most of the structure is underwater. It's a bit like an iceberg. So right up at this height, I'm actually exactly the same height as the top of the Empire State Building. An offshore platform like this is really a chemical plant at sea. And because it's an industrial plant, that's why I'm wearing yet another set of protective clothing. Down there is the gas plant, and in the distance, the grey section is for processing the gas, and here in the middle is the drill rig. This new platform hasn't finished drilling all its production wells yet. There are going to be 39 in the end, down into the seabed, and then fanning out to a depth of about 1.5 kilometers. They reach out for half a kilometer all round the platform. Above us are the drill stems, hanging like in a wardrobe, ready to be used. On average, it takes a month to drill each of the wells to extract gas. But what we're really interested in is what makes this structure stand up. And to do that, we need to go down to the seabed itself.
The journey down to the bottom of the sea is by a lift inside one of the great legs.
It's so quiet, it's really eerie. You have the feeling that with the sea outside, you're just on another planet.
On land, you see tall buildings, you see tunnels, you see other gigantic structures. But here, in this environment, the scale of this engineering and its achievements are really extraordinary. You really feel there isn't anywhere on this planet or any other planet we couldn't go. The pressure of the sea outside, just outside the wall, is 30 times the pressure inside here at the bottom where I'm standing, trying to squash the leg like this. The reason it can't is a combination of the strength of the heavily reinforced concrete and the cylindrical shape, which is the most efficient shape to resist that sort of external pressure. Just the same principle as a submarine hull or an aircraft fuselage. Down here, right at the very, very bottom of the platform, is where the pipelines turn the corner and head out over the seabed, taking the gas to Norway, 60 kilometers away, down there. And under my feet, there's a concrete floor, and under that is the mud. And the whole platform is embedded deep into the seabed. It's like a bunch of upturned coffee cups, 19 of them, and we're just in one of them. And they've been pressed into the seabed with the wall of the coffee cup pushed deep into the mud. And if you can imagine pushing a mug into mud, trying to pull it out, the suction inside holds it firmly in place. And that's exactly how this base works. Bit of a leak over there. Hope it's not too serious. No, it's just a leaky valve, really. Just collecting up some water. This might look like graffiti, but actually it's the visitor's book. And I've been invited to sign my name. There. I'm back on the main deck level, at the top of the concrete legs. Down on the seabed, the problem was to withstand the huge pressure of water. But up here, near the top, it's the forces from the wind and the waves pushing on the platform. It's a quiet day today, but in a storm, waves can reach the deck right up here, 30 meters above sea level. That must be pretty frightening.
But the deck is high enough to avoid being swamped by the waves and is securely attached to the 4 great concrete legs, which are strong and stiff enough in bending to withstand the estimated 5 million waves that crash onto them every year. It's structures like the Great Troll platform and the engineering advances behind them that give us the confidence to know that we can live and work alongside the sea, whatever the conditions. It's no longer a question of seeking refuge from it, but of knowing we can coexist on shore and in the deep oceans.
There's one structure which has endured since ancient times, an essential element of buildings and bridges alike, the arch. The arch's strength lies in its shape, and over the years it has proved one of the most reliable forms of construction known to man.
In this program, we travel to Cologne Cathedral to explore the Gothic arch, and to Hamburg to see how, using modern materials, arches have evolved. But we start with the civilization who were the first to really exploit the concept of the arch on a large scale, the Romans. This is the magnificent Pont du Gard near Nîmes in the south of France. Upon seeing the bridge, the 18th century philosopher Jean-Jacques Rousseau said he felt lost like an insect in the immensity of the work. It formed part of an aqueduct 50 kilometers long, which supplied water to the Roman town of Nemesis, now known as Nîmes. It's the highest bridge the Romans ever built.
It's an incredibly striking structure, 48 meters high, with 3 tiers of arches to carry the aqueduct at the top across the river. These are classic semicircular Roman arches. In all, there are 6 across the bottom level, 11 in the middle, and 35 across the top. The longest span is 24.5 meters, among the longest spans of any bridges built by the Romans.
The aqueduct was thought to have been built during the 1st century AD and was needed to cross the river Gar, a tributary of the Rhone. With arches, the Romans discovered a simple and effective method of bridging space. But the valley was much too wide to be crossed by a single span, so the Romans solved this problem in the highly practical way that characterizes many of their major building works. The aqueduct simply consists of lots of arches which together bridge the valley. You can see that a footbridge has been built next to the aqueduct, almost doubling its width. This was done in 1747, and its stone arches exactly echo the originals.
In fact, it's quite a sympathetic add-on, and it doesn't detract from what we're here to look at. The arch itself is made up of these stones here. They're all slightly wedge-shaped, and together they form a semicircle from this pier to that one over there. Stone cracks easily when it's pulled apart, but when it's compressed, it's immensely strong. The arch works because each stone pushes against its neighbour, and the weight is carried outwards and down. When the forces reach the end of the arch, they're taken down the pier to the ground.
The thickness of the stones making up the arch are crucial to whether it stands or not. These are over a metre thick, approximately a 20th of the span of the arch. The Romans never made sophisticated calculations, but they knew from experience that if the stones were any thinner for an arch of this size, the arch would be at risk of collapsing.
Once built, an arch is incredibly strong. It can support a lot of additional load on top, but the weight has to be spread across it, and that's what these solid parts are for, called spandrels. The spandrels are not part of the arch, but they just transfer the loads from above into it. So it doesn't matter what they're made of, and behind this stone facing is just compacted rubble filler.
The Romans were expert builders, and the Pont du Gard must be one of their greatest achievements, especially when you consider that the technology available to them was limited.
The arches were built on wooden scaffolding, which carried the weight of the stones until the last stone was dropped in at the top, the keystone. Once the scaffolding was knocked away, the arch would stand, hopefully.
Although these arches are among the largest the Romans ever built, their span was restricted by their equipment.
The stones were lifted up into position using wooden cranes worked by teams of slaves. The biggest crane the Romans had could only reach around 15 meters. So if you had one crane on each side, the biggest arch you could build was less than 30 meters.
At the top, the water channel is just 1.25 meters wide and over 1 meter deep. It's the only part of the aqueduct that uses mortar, needed for waterproofing. Originally, it would have had a stone roof, but much of this is now missing.
Looking along the aqueduct, you can see that it's developed a curve towards the upstream side. This is because, over the centuries, undermining of the piers has caused the bridge to lean over ever so slightly. But masonry is extremely robust, and it would take much greater movements than these to cause it to actually collapse.
The Romans' major contribution was in the construction process, the organization and techniques which were used, rather than the development of new design concepts. The Roman engineers learnt from experience, setting out their arches using geometrical rules. This system was highly effective, perfectly suited to their needs, and the Pont du Gard is the finest expression of this. The Pont du Gard is a celebrated object of beauty, a remarkable piece in the huge jigsaw of Roman engineering. They were the first civilization to understand the value of the arch, and their use of it as a fundamental building block in much of their construction is an enduring part of their legacy. This aqueduct and the other structures they created across Europe are a lasting monument to their skills. The fact that bridges such as the Pont du Gard still stand is also a testament to the strength of the arch. Once built, they will pretty much stand forever, or until the stone finally weathers away. But over the centuries, changes in building styles have forced the arch to evolve. Nearly 1,000 years later, in a new phase of monumental construction, the arch found a major new expression. The 12th and 13th centuries in Europe saw an extraordinary explosion of architecture and engineering, driven by merchant wealth and religious fervour. This was the High Gothic Age. Many of our greatest cathedrals date from this period, including this one, the imposing Cologne Cathedral in Germany. It has a highly decorative, even extravagant exterior, but all this decoration is actually concealing quite a simple structure of arches and vaults, which owes much to the Romans. Like the Pont du Gard, the structure of Cologne Cathedral is entirely based on arches, but the crucial difference here is that the round arch has been replaced with a pointed arch. This was a vital development which allowed a different form of building altogether, a building which was light and spacious, but above all, which was high. All this was achieved because the pointed Gothic arch carries the weight more directly to the ground. It's a much more efficient shape, so it can be much thinner. In addition, the symmetry of the arched vaults and the clean vertical lines of the piers give Cologne Cathedral its particular elegance. Cologne Cathedral has its roots in the great French cathedrals of Notre Dame and Amiens. The choir here at the East End was started in 1248, but it took another 600 years for the towers at the West End to be finished. In reality, work on this building never stops. There's a local saying, which loosely translates as, "When the cathedral is finished, the world will end." In the great cathedral building boom, new skills and techniques evolved. Stained glass windows and high arched stone ceilings grew ever wider and more magnificent as towns and cities tried to outdo their neighbours. That these structures have lasted nearly 1,000 years can be attributed to the knowledge and experience of the stonemasons who built them. Stone was shipped down the Rhine from the Drachenfels, 40 kilometers upriver. The master mason supervised the whole construction, combining the modern role of engineer and architect and organizing the teams of professional craftsmen on site. They were highly sought-after men. Cologne Cathedral was laid out by Master Gerhardt, who had visited France, where he studied the techniques used in building the French cathedrals. By the time of his death in 1260, the cathedral was beginning to take shape. Although many master masons followed Gerhardt, it was his vision which we see in the layout of the cathedral.
The rules of proportion used in the design were originally developed by the Greeks and were handed down from generation to generation in the Masonic lodges. It wasn't until much later that people began to understand, in structural terms, why they worked. What the masons knew was that a building built strictly according to their geometric rules would stand up.
But building this high created new challenges. The weight of the roof on the tall vertical piers pushes them outwards, so the piers have to be supported in some way from the outside.
Because the cathedral is so much narrower at the top than at ground level, where you can see all the extra space in the aisles, the supports for the roof have to span right over the lower level. So a new development was needed, a Gothic invention, the flying buttress.
All around the perimeter of the cathedral, the upper levels are supported using these flying buttresses. In fact, these are flat arches, and they work very effectively.
The force outwards is concentrated where the roof and the vault meet the pier, here. The force is carried down the arch, like this, and the weight of the buttress directs the force down to the ground and stops it toppling outwards. The pinnacle is also a nice detail. It adds weight to the top of the buttress to stop the arch breaking it off.
The cathedral has survived through some difficult times. There was damage during the Second World War when 10 vaults in the nave and north transept collapsed. One bomb damaged the tower so badly that it had to be bricked up, and it has been left deliberately in this condition as a reminder of those years.
There's currently a major program of restoration underway. Many of the pinnacles have been repaired, including that one, the top of which fell off in an earthquake in 1992. There's also a plan to protect and clean the whole building, but without changing its overall appearance.
Over time, pollution has turned the cathedral almost black, and this has given it an almost foreboding appearance. Nevertheless, Cologne Cathedral still remains remarkable in its details and awe-inspiring in its scale.
With just simple hand tools, wheelbarrows and winches, the builders of these Gothic cathedrals realized the most complex industrial projects in Europe since Roman times. Their organization of the site itself into teams of paid professionals rather than slaves was fundamental to their success. But for me, it's what they achieved technically in a pre-scientific age that's so extraordinary.
Because of their strength, steel and concrete have now largely replaced stone as a building medium. But where great spans are needed, the arch is still an extremely attractive solution. This is the jumbo shed built for Lufthansa Technik, the engineering wing of the German airline. It takes 3 planes, including 2 747s, and is one of the biggest aircraft hangars in the world. Forming the heart of a base here which employs over 5,000 people, it was opened in August 1992 at a cost of 172 million marks, over 60 million pounds.
The design of this enormous hangar posed some real engineering challenges. Lufthansa wanted to be able to open the whole of the front of the building to get the planes in and out easily. Secondly, the height of the building is restricted by airport regulation. This meant the roof had to be supported in a rather special way.
Instead of columns underneath, 2 huge steel arches hold up the front of the roof. The roof frame is suspended from the arches by hangers, rather like the deck of a suspension bridge. The arches are positioned towards the front of the building because the doors can't carry any weight, but the back of the building is held up on ordinary columns.
The arches span 180 metres from one side of the building to the other. They sit on 4 A-shaped supports, 2 at either end of the building, and the arches get additional stability by leaning together and being joined with struts. Just crossing the threshold through these huge doors and into this giant hangar, it's quite spectacular. A jumbo jet is 7 stories high, but it's dwarfed by the height of this roof. This one's covered in platforms and machinery, spaces for men to work. This is where the third plane goes, right here.
The hangar is used to service primarily jumbo jets. Working 18 hours a day, it takes 7 weeks to totally refit a plane, and it costs £3 to £4 million, not counting the engines or the paintwork.
The construction of the building was quite ingenious. The whole roof, with the arches, was built out here on the ground, while the foundations were laid on site, saving time and money. The roof was then slid on rails into its position and lifted up using hydraulic jacks onto the A-frames on either side.
The arches are simply massive. Together with the roof, the whole weight is 2,800 tons. That's the weight of 18 empty jumbos. You can see the struts joining them together. This gives them a lot of rigidity, stiffening the whole roof from sway from wind loads pushing the building sideways.
The hangars are inclined from the arch down to the joints here where they meet the roof frame. This is to keep them in line with the frame, which runs straight along the building. The hangars distribute the weight of the roof along the arch, just like the spandrels on the stone arches we saw at Nîmes. This arch is much longer and flatter than the rounded arches at the Pont du Gard or the pointed Gothic arches in Cologne. And you can see there are no buttresses on the outside of the building. So how does this arch stand up?
It's an ingenious solution. The arch is like a bow on its side, and the roof frame acts as the bow string, tying the ends of the arch together.
Here at the end, the force down the arch meets the support, and the arch tries to push outwards. This steel link ties the arch to the roof frame, which you can just see sticking out of the building. The push outwards creates a pull in the roof frame right through the building. This is the bowstring effect, which allows the arch to sit on these flat bearings here without a buttress. We're right underneath the roof here and right on top of the jumbos. You don't often get to see them from this angle. It's the workhorse of the world, the 747, and it gets refitted every 6 to 10 years. This one's nearly finished. Another 5 days and it'll be off to the paint shop. The roof frame itself is made up of trusses which run along the building and across. This is one of the 2 which are connected to the hangars up above. Being this big gives the roof the stiffness it needs to support the cranes which carry engines and other heavy equipment around down there. This is one of the access platforms underneath the roof. Can we go down, please? Get a great feel for the size of the hangar here.
The hangar in Hamburg is a prestigious building, a centerpiece for Lufthansa's technical operations. It's a structure in the public eye, a showcase of engineering confidence, clearly visible to the passengers in planes taxiing by. The great space could have been bridged using more standard beams and trusses, but the result would have looked like an industrial shed. The arch, as always, has a natural beauty.
The arch is a pure and simple form. As we've seen at the Pont du Gard in Cologne and here, it derives its strength from its shape. That shape has evolved over the centuries as new materials and our understanding of its behavior have developed. As well as a glorious past, the arch has a great future.
Here, in the shadow of Mount Vesuvius, near Naples, is where the Romans invented modern concrete, a material which was to shape the course of their monumental architecture.
In this program, we visit France to explore the stunning Plougastel concrete arch bridge at Brest. We marvel at the breathtaking design of the airport railway station at Lyon. But to discover the Roman origins of modern concrete, we need to start in Italy.
Early concrete had been used by the ancient Egyptians and the Greeks, but it was a chance discovery here by local builders using these volcanic soils that led to a critical new development in the history of construction.
Concrete is made by binding sand and stones together with an adhesive which is called cement. Early Roman builders had made basic cements using lime, sand and water with some success, but across the bay, near the Roman port of Pozzuoli, builders found that their concrete had a much greater strength than anyone else's.
The secret? They discovered that by using sand from the volcano rather than ordinary beach or river sand, they could create a much stronger material. It would even set underwater. By the middle of the 1st century BC, the new cement, named Pozzolana after the town, had become a key element of all major Roman construction.
The Romans didn't understand the chemistry, but the volcanic sand changed the chemical reaction in the setting of the cement. It's this that gave their concrete its special properties. Their new discovery was a concrete of unprecedented strength, and it heralded a new era, paving the way for some of the greatest buildings of the Roman Empire. This is the amphitheatre at Pozzuoli, the town where the new concrete was first discovered. Begun under Nero and completed just before the famous eruption of Mount Vesuvius in AD 79, the building has stood for nearly 2,000 years. We're here because it has some of the best preserved Roman concrete work anywhere.
The amphitheatre is a great oval shape, 149 metres long and 116 metres wide. It could seat 20,000 spectators. It was used primarily for fights between gladiators and wild beasts, which were kept in rooms underneath and lifted up into the arena through hatches in the floor.
On first glance, it looks as though the amphitheatre is built entirely from brick and stone. But this is deceptive. In fact, the bricks are largely just a facing.
These walls are made of concrete with a tile or a brick facing. The concrete was made in a stiff, wet mix and placed by hand in position. The tiles on the outside and on the inside were to stop the concrete slumping outwards, providing just enough lateral support for the relatively short time it took the concrete to set. That way they could build the whole wall up continuously.
Cement actually works because chemical reactions form crystals when water is added to the dry mixture, and these stick to everything they touch. It's a bit like wet sugar, which when it dries gets sticky. It can stick a spoon to a saucer, for example, like this one. Like modern cements, the Roman pozzolana actually absorbs water during this crystallization process, which is why it can set underwater. Concrete gets its strength from the cement, but also from the mixture of stones inside it. Down here, you can see concrete with some quite large stones in it. The different sizes of sands, gravels and stones means that the whole mixture becomes interlocked and dense when it's compacted. The smaller stones simply fit between the larger ones, and the cement glues it all together.
As well as walls and foundations, the Romans realized that their new concrete could bridge spaces. Domes and vaults became less expensive and simpler to construct, leading to a new and grand architecture.
To build a vault like this, wooden shuttering would be constructed underneath and the wet concrete poured or placed on top. The shuttering had to be very strong because it had to carry the whole weight of the roof until the concrete had set. Sometimes, if the wooden planks weren't perfectly smooth, they would leave lines in the roof showing where the wooden supports were positioned.
In their buildings, the Romans used brick, stone and concrete together for both decorative and structural reasons. But because concrete can be molded to any shape, it is often used largely as a structural filler, hidden behind brick and stonework. Because of this, the extent of the Roman use of concrete in their monumental buildings is still not well known.
Perhaps the greatest advantage of concrete over the earlier building materials like brick or stone is that all you had to do was to bring the loose materials to site and mix them with water. Like all construction, even today, the cost of bringing materials from a long distance, like stone from a quarry, can be huge. If you can use local sands and local gravels and mix them together in a bucket and make a new material that's nearly as strong as stone, but in any shape you want, that's concrete. The Roman process of making concrete wasn't bettered until the 19th century, when a deeper understanding of the chemistry of concrete allowed modern cements to be developed. But the principles of modern concrete are exactly the same, and the next major evolution was to discover how to reinforce concrete to make it even stronger, as we shall see next. During the second half of the 19th century, a new concept emerged, which was to transform the character of architecture and civil engineering, indeed of all modern construction. It was to reinforce plain concrete with iron or steel, creating a new material with properties which combine the best of both.
Here in Brest, in northern France, is the Pont de Plougastel. Completed in 1930 by Eugène Freycinet, it broke all records for a concrete bridge. It's an extraordinary monument to Freycinet, a brilliant civil engineer and one of the pioneers of reinforced concrete.
It comprises 3 huge concrete arches, each spanning 190 metres, with a double deck across the top designed for road and rail traffic. The arches are high too, with a rise of 35 metres in the middle to allow ships to pass underneath.
In the 1980s, it was decided that it was too narrow to be upgraded as a motorway bridge, and a new cable-stayed bridge runs over the river nearby, leaving the old bridge for pedestrian and cycle traffic.
As we've seen, the use of concrete as a building material can be traced to early civilizations. But it was only during the 19th century that it was realized that by embedding iron bars deep enough in a concrete, they would be protected from rusting, and it would create a material with strength and durability for really large structures. This is a piece of old reinforced concrete, and you can see the steel bars sticking out the end. In fact, they run right along the length of the beam, buried inside the stone. These have rusted because they're exposed to the air, but inside they'll be as good as new. Although concrete is extremely strong when it's compressed, it cracks easily when it's stretched. The idea of the steel reinforcement is that it carries the pulling or tensile forces in the concrete. It's a very efficient system because the combination of steel and concrete working together is much stronger and stiffer than either of them working independently.
The Plougastel Bridge was a turning point in the use of reinforced concrete. Prior to this, it was simply not believed that it would be possible to build a concrete bridge so big. Freycinet argued that a concrete bridge would be less expensive and lighter than a steel bridge. He was also convinced it would be strong enough.
By the 1920s, Freycinet had learnt how to compact his mixture of stone, sand, cement and water to make a concrete with a strength of up to 50 newtons per square millimetre. That's as much as some rock, and more than twice as much as had been possible at the turn of the century. Reinforced concrete is made by pouring concrete into a mould in which the steel reinforcement has already been positioned. To do this out over the river was a real challenge. He designed a huge wooden arch resting on concrete pontoons, like this, which could be floated out into the river and was used as a mould for the concrete arches, which he built one at a time. The sides of the arch were built out from the bottom, like this, until they almost met in the middle. Freycinet's trick was to leave a gap at the top and to wait for each side of the arch to set. Then, using hydraulic jacks, he lifted the arch off the mould and into its final position simply by pushing apart at the top. After he filled the gap, he constructed the vertical supports and finally finished the deck. And now I'm underneath the deck. This is where the track for the railway would have run if it had been completed. We're right inside one of the big arches, stretching down here, right to the bottom. You can see the arch stretching out down there, getting steeper as it goes. It's a hollow box structure. Because it's made of reinforced concrete, it doesn't have to be solid like a masonry arch. These triangular pieces are where the vertical supports for the deck above meet the arch. Down near the bottom of the arch, it really gets quite steep. That's the bottom just there. And that's the sea. The Plougastel Bridge was also the key to another of Freycinet's innovations, for which he's best remembered. After this bridge, he subsequently developed a system of pre-stressing concrete, which gave it even more strength. This enabled the construction of pre-cast units, which could simply be lifted up and assembled in place. And that's the method they used for the new bridge.
After nearly 70 years, the bridge is beginning to decay, but we can't expect it to be pristine, and sometimes, like here, the water can get in along tiny cracks and rust the steel bars, which then expand and spoil off the concrete. It's a bit unsightly, but it's not serious. Despite its appearance, this is an historic bridge. It's a strong and confident design, a marvelous expression of a bold engineering spirit. In building the Plougastel Bridge, Eugène Freycinet had made a huge leap in fulfilling the future potential of concrete. Over the following years, the use of reinforced concrete quickly became widespread. Free to mold the material to their designs, architects and engineers around the world could finally create new shapes which were also inherently strong.
More recently, we've come to think of concrete as a mundane, even dull material. Tower blocks and car parks from the 1960s and 70s have put a lot of people off. But it can be quite magnificent. And for me, there's nowhere more exciting to see just what you can do with concrete than here.
This is the Satellas TGV railway station at Lyon Airport in France. Commissioned by regional government and the French railways, the building was designed by the great architect-engineer Santiago Calatrava. It's a prestige building which cost nearly £15 million, but the result is a station that is simply unique.
Completed in 1994, the station was the subject of an international competition. Its importance is apparent from its design and its location. It stands squarely across the main access road to the airport, which has to run straight through it.
The complex forms a strategic transport interchange for the whole region, incorporating the airport, a nearby motorway, and the main railway line on which the station stands.
To the side are the tracks for the stopping trains, and in the middle are the high-speed TGV lines, these ones here. These through trains run at 300 kilometers an hour, so they're segregated from the others, running in a tunnel to protect the people in the station from the noise and shock waves.
Approaching the building, it is immediately apparent why it has achieved such prominence. There is an extraordinary quality to it, a feeling of dynamism and movement, almost uplifting. The whiteness of the concrete mix makes it look even more like a sort of skeleton, fused onto the foundations below.
Spanish-born Santiago Calatrava studied sculpture while reading architecture and later turned to civil engineering. In a relatively short career, he's become well known for his outstanding design of buildings and bridges, structures which combine the functional and the aesthetic, and which, like this one, have sculptural qualities. Under the great winged section in the centre is the main concourse with its magnificent steel and glass roof. There are some wonderful details. But what I want to show you is Calatrava's use of concrete and for that I need to find the platforms.
Unpainted white concrete ribs stretch over our heads, looking like the vaulted roof of a cathedral, but with openings which create dazzling patterns of light and shade all over the floor. You would never have thought of building a white station in the days of steam trains.
As we've seen, reinforced concrete has strength in bending as well as compression, and this is where we can see that used to best advantage. The curved shape of the roof, and particularly the tapering props on either side, reflect precisely the forces they're carrying. They're thicker at the top, where the bending forces are greatest. This aspect is why people have commented on the natural quality of this design. But to see the whole structure, we need to go outside. The choice of concrete is quite deliberate. It feels solid and substantial, but it also gives the building weight and stiffness to cope with the dynamic forces generated by high-speed trains passing behind that wall.
But there are many aesthetic details here too, which are unusual in concrete. These great inclined legs on the outside support the edge of the roof, but their shape is carefully echoed on the opposite side, right along the central wall. It is this attention to detail which really characterizes good design.
The handrails show us just what a marvelous material concrete can be. Here you can see the true nature of concrete, reconstituted stone. The finish is absolutely superb, as are all the other structural details.
Calatrava is a master of elegant structure, blending art, architecture and engineering. With the TGV station at Satolas, he has brought the use of concrete forward into an artistic perspective, creating shapes of great beauty out of a material we most often associate with simplistic and functional buildings. In the hands of a master, concrete can be a marvelous material.
To take stone and fuse it together with a cement was an ingenious idea. To add steel reinforcement allowed engineers to create a material which was extremely versatile. Made with care and attention to detail, concrete can also be stunningly beautiful. It hasn't all been plain sailing, but here, finally, concrete has come of age.